Hello. So in this section, we are continuing our work on graphs, and we're going to look at more graph transformations. So things that we could do to basically change the graph, essentially. So last time we looked at translation, where, as an example, say if we had x squared, we could shift it to the right by a units, for some amounts, a units, say, and so it'd look like that if it's a there. And if the original curve is f of x, we discussed that this was f of x minus a, because I want to do the opposite. Because if I want to add a to my x values, my x coordinates, in order to move it to the right by a amounts, I need to do the opposite in my function. So instead of adding a, I'm going to subtract a, okay? And likewise, I could also instead move up and down. So if I wanted to then move up, say by a amounts, it would then be a there, and we can move up. And so then we said that this would be f of x plus a instead, where we add a to the y, which allows it to move up by a. So that was translations. And I also discussed here that the philosophy was that whatever you do inside the function, you do the opposite to what you expect. So again, with this example, you'd think you subtract a from x, but in actuality, I'm adding a, right, to move it up by a. Whereas if you have something outside the function instead, and something you're doing outside, so if you add a, that's outside the function, okay? So that'll affect the y value, and you do what you expect if you're outside the function. So you'd think we would add a to our y values, but that's exactly what we do, and that allows us to shift the curve upwards. We're going to be using that philosophy again within this section. Anyway, so that's a brief recap. So now we're going to look at stretching graphs. So let's have a look then. So let me pull up my example function again. So let's say we have x squared here. Okay, now what did we do last time? Last time we considered if we added numbers, right? So if we then firstly added x, right, we would have f of x minus a, right, in order to move it a units to the right. Oh. And likewise, we then added outside the function to move a units up, right? So the whole idea was last section we looked at adding and subtracting numbers in order to move it left or right, up and down, right? So that's translation. Now, what if instead of instead of adding and multiplying, oh, I gave it away there. Instead of adding and subtracting numbers, what if instead I alter my function by instead of multiplying or dividing? What if I have instead ax? Oh no, sorry, a f of x, so the a is outside the function, or I have ax inside the function. Okay, so what if instead I'm multiplying a number to x or y, okay, to the inside the function or outside the function, instead of adding or subtracting numbers instead? What is that going to look like? Well, again, if we use our philosophy, what does this mean? Okay, what would this mean, right? So using our philosophy that we just discussed, that we talked about last section, if we have ax, this is saying what would we expect, right? Let's do it here. F of a of x. What would you expect would happen? You'd multiply the x coordinates by a. Okay. So as an example, let's stick with x squared, but I'm gonna label some points on it, right? That I think will really help. So we have the origin here, then we have this point 1 here. Now the y value would be 1 as well, because that'd be 1 squared. Then we have 2 here. Then that would be let's move the 2 there. No, 1 would be there, 2 would be there. Okay. And then so that would give me 4, right? As a y value, because 2 squared is 4. Then lastly, if we did 3, then up here I'd have 9, right? Because then 3 squared would be 9. So those 3 points will help me understand this. So okay, AF of x. What if? Okay, let's think of an example first before we generalize it. So what if we had f of 2 of x, right? A is 2. What would you expect? The x coordinates to double, right? Now, our philosophy is what we do inside the bracket, we do the opposite to what we expect. So instead of multiplying by 2, this is going to divide the numbers, the x values by 2. So the x values by 2, right? So in that, with that in mind, then if we then sketch the graph again, but this time we do f of 2 of x. So this will be f of x, right? F of x is x squared. Now f of 2 of x. Now in this case, I'm saying I want to divide the x values by 2. So let's have a look at these 3 points that I've done. Okay, that I've circled there. So so the x value, the x coordinates have to divide by 2, because that's what we do. That's the opposite to what we expect. Instead of multiplying by 2, because we have 2x, we're going to divide by 2 instead to do the opposite. So first of all, this point is 1, 1. Well, the x coordinate's 1, the half of that's going to be 0.5, isn't it? So it's going to be 0.5 instead. But the y value will still be 1, because the y value is unchanged. Okay, it's just the x value that's changing. So the point would still be there at 1. Then what about the next point here? 2. Well, 2 is now going to be halved to 1, because then we divide by 2 again. So that's 0.5. 1 would then be there, right? So that, and then again, that y coordinate will still be 4. Okay. Okay, cool. And then lastly, this last point here, up here. Now the x coordinate of that point is 3, right? Well, the x coordinate is going to be halved because we divide by 2, so it's now going to be transformed to 1.5. Okay. And then the y value will still be 9 because that's unchanged, so it's going to be up there somewhere, right? If we extend the graph a little bit, there we are. So this is f of 2 of x. Now, we can, this will still resemble quadratic, so we can draw the quadratic curve that goes through these points, so it's going to look like that, and then it's going to be symmetrical, so it's going to again look like that, okay? So what do you notice here? What's the difference between the original graph here and the graph that I've drawn here? Well, the x coordinates are halved. That's the only thing I've technically done. The y values will still be the same, but the x coordinates halved. But what's happening is it's this kind of compression effect. It's like what I'm done essentially to the original graph is I've pushed the graph inwards from the left and the right. That's what I've done. If you imagine you're pushing, if you imagine surrounding the curve, right, and then you're kind of like you're basically pushing. Using your hands, right, either side of the curve that I've drawn, and then what you'd expect the curve to like squash, wouldn't you? You'd compress it, and that's the effect you've done here. So if you compress it by like a factor of 2, this is the curve that you get, okay? And so actually, what we call this is a stretch, okay? This effect that if we divide or multiply coordinates and transform it that way, that gives a stretch of the graph, okay? So in general then, if we hit, that's f of 2 of x, f of a of x then, if we do it up here, that's going to divide the x values by a, but also, if it's divided by a, that's the same as multiplying by 1 over a, isn't it? And that'd be the exact same thing. Okay, so that's a of x. Cool. And actually, the technical language we use is because it has this sort of stretching effect, we call this a stretch horizontally, right? Because imagine we are pushing the curve inwards from the left and the right side. That's a horizontal effect, right? Because it's left or right, it's a horizontal effect, right? And it's horizontal because it's obviously acting on the x. If it's acting on the x values, the x-axis is horizontal. This x-axis, right, is a horizontal line, so it would be a horizontal stretch, we call it. So it's a stretch horizontally, which is a fancy way for saying it affects the x values, essentially. So it's a stretch horizontally by scale factor 1 over a. And these two mean the same thing, essentially. But I think this one's a bit more simpler and easier to understand. But technically, this is what this notation means. F of a of x, instead of multiplying by a, you're dividing by a. Or in other words, you're multiplying them by 1 over a. And that means if you're basically dividing all the x values by 1 over a, you have this sort of stretch effect. Whereas horizontally, you're kind of pushing the curve inwards by a scale factor of 1 over a. And yeah. Okay, so let's have a look at what we do if we have it outside the function instead. What if instead we had, let's do it over here. What if we had 2f of x instead? Well, obviously f of x again is this original curve. Well, again, what would you expect? The y values would double, right? Because you're multiplying 2 by f of x. And remember, f of x is just y as well. So if you have 2f of x, that's just 2y. Well, hopefully you can see that means there, doubling the y values, if that's how it makes you think. But yeah. So the number is outside the function, so it affects the y values. So we do what we expect. If it's outside the function, we discussed this last time, you do what you expect with the transformation. So you're going to double the y coordinates. So let's do it with this curve again. So let's draw my axis here, x and y. Well, so let's again with these sort of transformations, it's best to visualize it, to transform some known points on the curve and then go from there. So let's have a look at these 3 points again. So this first point 1 1, well, the y coordinate's doubling this time, so it's going to be x is 1, that's unchanged, but the y would then be 2 to double it, so it'd be about there-ish. So there we are. Okay, what about the next point, 2 4? Well, 2 4, well, the y coordinate will double to 8, so it's going to be up there now, right? So it's going to, and then it'll still be 2 for the x coordinate. So therefore we would get the point over there, okay? Then lastly, the last point here, which is 3 9. Well, the x coordinate will still be 3 there. But the y coordinate of 9 would double to 18. So actually it's going to be all the way up here, isn't it? If you imagine 18 to be there, if you continue the y-axis, somewhere about there. Okay, but then if we connect the points again by a quadratic curve, so it's going to look like that, and then we do the same on the other side. Well, that's our quadratic curve. And actually, again, they're actually very, very similar, these two graphs here, these two. The f of 2 of x and the 2f of x are pretty similar because they're both stretches, right? They're both stretching the graph, but they're doing it slightly different ways because obviously the coordinates are different between f of 2 of x and 2f of x, right? And actually, I should make that a bit clearer. Let me continue the y-axis then. There we are. So 18 is there. Okay, cool. And this is 2f of x. Okay, so they're very similar, but the stretching is slightly different. Because this one is acting vertically. It's affecting the y values. So the y values are doubling this time. But they produce a very similar, but not the same effect. Because again, these coordinates here, and these coordinates here are all different. So they are different even though the graphs look similar. In the fact that they've been stretched or compressed, I guess, but there's we call it a stretch. Okay. Yeah, and if you imagine instead of going from left to right, this time, because it's acting vertically, we're kind of pushing the graph upwards instead. So this graph upwards, right, to kind of bend the graph up more steep, to make the graph more steeper by pushing it upwards like this. So it has a similar effect, but it's not the same. So because of that, we can then generalize to say AF of x, obviously this was when A was 2, but AF of x for any function x, we are multiplying instead the y values, okay, and it will be by A, okay, because that's what you expect. We're not divided by A, we do exactly what we expect, we multiply by A, because we're doing A multiplied by f of x, which is y. So you do exactly what you expect in that case, because it's outside the bracket, remember. Cool, and therefore we can also say formally this is a stretch vertically, because vertically is in the y direction, and that's by scale factor A, so that's the language we use. So again, that's a fancy way of saying we multiply the y coordinates, or go upwards by y, by multiplying by A, essentially. But we'll have a look at that in more detail as we go on. Okay, cool. So the last thing is, and actually it's using the set what we just learned, but there's two more specific types of transformations. So if I again, let's stick with do, do, do. What should I do? Yes, let's do this first. So let's stick with x squared first of all. Okay. Now, what happens very specifically when we have minus f of x? So x squared is f of x, as we just done as an example. What happens if you have minus f of x? The minus is outside the brackets, the f of x, the function. Wow, that's effectively times it by minus 1, effectively. So what if we use what we just done here? AF of x to a is minus 1. So that's saying we multiply the y values by minus 1. Well, if we multiply the y values by minus 1, so xy becomes x minus y to make the y minus 1. Well, you're just flipping the sign of y, aren't you? The only thing that's really changing in this graph here is the y values flip side. The positive y values become negative, and the negative y values become positive, okay? So let's do that then. So let's plot out of this minus f of x graph, see what happens. And again, we're going to take some points. So let's take this point here, that point there, and this point there, okay? And we'll take the left side as well, actually. There we are, cool. Okay, but let's start with the origin. Well, the origin 0, 0. Well, y 0, so it's still going to remain 0. Flipping minus 0 is the same as positive 0, so it will remain where that is. What about this point then? Should say that's 1, 2, 3, but it doesn't really matter. But this point is 1, 1. And I'll label this, it's 1 there, 4 there, and 9 there. And that's a minus 1, minus 2, minus 3. Anyway, so I've just given the values for these points. Anyway, so this point I've circled is the coordinate 1, 1. Now the x coordinate will still be 1, but the y coordinate will change to be a negative, right? Because again, it's outside the bracket, it affects the y. So we times in by minus 1, so that means it'll go 1 here, but it'll go to minus 1 down here, okay? So all I've done is the y value of positive 1 here gets multiplied by minus 1 to get minus 1. So we're just flipping the sign. But again, the x value will still be 1 because I'm not changing the x value, only the y value here. Because the input inside the function is still x. I've not changed x in any way. So that's my first point. What about this point then? This point I have 2 and 4. Okay, well, it'll still be 2 for x, but y from 4 will then be minus 4 if you times by minus 1. So it'd be down there, and it'll be about there, right? Roughly. Then what about this point then, at 3, 9? Well, 9 would be -9, so it'd be down there somewhere. And it'll still be at 3. So there we are. Oh, there we are. Cool. Okay, so we've got some points. What about this point then, on the left? Well, this is -1. Let me fill in this axis. That's -1, 1. Okay, so x will still be -1, but y would then be from 1 to -1 if you flip the sign on the y, so it'd be there. Okay, so that point I've circled moves to that point there. When I apply that transformation of -f of x. Okay. Okay, what about this next point? This is -2, 4, right? I should make this a bit clearer, hang on. -1, -2, -3, there we are. That's -2, 4. So -2 will be the x value still, but 4 will then turn to -4 down there. And then this last point here, -3, 9, well, it'll still be -3 for x, but then it will go to -9, because 9 times -1 is -9. Okay, but now we've got a really good idea for what our quadratic would look like by going through all these points I've circled here. So let's draw a quadratic curve again, okay? Cool. Okay, and then now what I'm going to do is I'm going to draw my original curve again. I'll draw it in a different colour to really help you visualise what's going on. There we are, cool. So what has happened in this particular case? So this is y is -f of x, and this was this green curve is the original function. Y is equal to f of x, right? Oh, what has happened? So what can you observe is different? What is going on with these two functions? What is the difference? What's the relationship? If you look at the graph, what is kind of going on basically? Hopefully you notice. Well, this is going up. This is in the positive axis, right? And but this is in the negative axis because all the y values are turned to negative. But hopefully more specifically, if you think about transformations, what do we have? We have reflection, we have rotation, we have enlargement, we have translation. Well, hopefully you spot out of those 4, I have a reflection. But what line is it being reflected under? If I get rid of this, let's make it really clear. It's this line here. This is the mirror line, right? The reflection line. Oh, if I can draw it better. There we are. Cool. That's the line of reflection. But what line is that? It is the x-axis. So what's going on here is when I have -f of x, the minus outside, that is a reflection in the x-axis, and that again is generalized. So what we have then is so what we have here is I'll try to work out what room I have left. Okay, so if we have y is -f of x, yes, that means we multiply the y coordinates by -1. But in this very particular case of a f of x, when a is -1, so we get -f of x. In this particular case, as we see here, that curve, so our graph, is a reflection in the x-axis. Okay, so actually with this stretching, I can actually get a reflection as well, a reflective transformation. Okay, so that's -f of x. Now, what's the other thing to consider? Well, we consider what happens outside the function. What happens if I put it inside the function? What if I have y is f of -x? Now, it turns out with x squared, it's the same thing because there's a symmetrical property, so there's no difference. So let's consider x cubed, okay, instead. So x cubed is here, and it looks like this, right? graph you should all know and love, right? So this is y is x cubed, or we can call f of x is x cubed, right? Okay, cool. And we need to know some points again to help us. So let's consider this. Well, we've got the origin here, and then this point would be 1, and then 1 cubed would be at 1 as well. But then if we have 2 here, 2 cubed would be 8. Actually, no. 2 would be up there somewhere. There we are, 8. Okay, and then I'm going to do the negative side as well, because obviously we're considering negatives. It makes sense to consider the negative side of the graph. So firstly, let's consider -1 here. So that would be on this point here, but then that will also be -1, because -1 cubed is also -1. And then -2 down here would be here, and that would be -8. Okay, so again, I've got some points to consider, right? Cool. I just want to make the numbers really clear here on my axis. So that's x and that's y. Okay, cool. So what I'm going to do then is consider sketching y as f of minus x. Now, as an expression, f of minus x, we basically, for f of x is x cubed, I'm substituting minus x in, so it'd be minus x cubed, which actually turns out to be minus x cubed, okay? Now, coincidentally, that's also the same as minus f of x, so actually in this case, it would be the same thing if we did it for the y-axis, for the y, we'll reflect it in the x-axis, but let's see what happens in this case, okay? By looking at this type of transformation. So, what do we expect to happen here? Because we have well, this is a specific case again of f of ax, where the a is inside the function. So we do the opposite to what we expect. So instead of timesing the x values by a, we divide by a. Well, in this case, a is -1, so we have minus f of x. Now that would mean we'd have to, instead of multiply by -1, we divide the x values by -1. But x divided by -1, that's equal to minus x. Well, that's the exact same as times it by -1. So in this particular case as well, divided by -1 is the same as multiplied by -1. So this is dividing or even multiplying in this particular case the x values by -1, okay? Or you want to be really fancy, this is saying a stretch horizontally by scale factor -1. Remember when we use this terminology? And you will see this terminology, so do get used to it. We will be describing graphs in this very particular type of terminology. But no, that's just a fancy way for saying this. Okay, that stretch vertical by scale factor a, as an example, is the same by multiplying the a of y values by a. Okay. Anyway, let's go back to our example. So let's sketch out a graph then of f of minus x. And what we're going to do then is also, again, consider what happens to particular points that we know on the original curve. Where would they go under the transformation? And that will help us really visualise what graph we have. So firstly, let's consider the origin again. So the origin is 0, 0. Well, x is 0. So times it by 0, by -1, sorry, still leaves it as 0. We've done nothing there, so it will stay at the origin. Okay, then we have this point here that I've circled. Well, this point is 1, 1, okay? Now, 1, 1, well, the x value is 1, so that would go to -1 there. And the y value will still remain at 1, so it would be there, okay? That's where it would move to. Okay, now let's deal with this point here. Well, this point is 2, 8. Well, again, the x value is 2, so by this, I'm multiplying 2 by -1 to get -2, so it'd be over there. And the y value will still be 8, okay, so it would be up there somewhere, right? Then we have these other 2 points down here on the negative side. So this point is minus 1 minus 1. So x is minus 1. So minus 1 times minus 1 will give us positive 1. Okay. So that's like two negatives make a positive, right? And the y value will still be at minus 1. So the point will be there instead. Okay. Okay, then what about this point here? Well, this point is minus 2 minus 8. So the x value is minus 2, the coordinate. But minus 2, if you flip the sign, would be positive 2. So it would be over there. And again, the coordinate will then be minus 8 for y. So it could be there, okay? As the y value is unchanged, right? Everything that changed is inside the bracket for f of x. So nothing outside, so the y value should remain the same. Okay, so then we have our graph there. Well, it's not very helpful because it looks like a straight line, doesn't it? But that's not what's going on. It still has to resemble this cubic. So what's going to happen is it's going to kind of... well, let's think about more points then to really help us. So what about this point here? We don't know what the value is, but we know that the y value has to remain the same, but the x value has to go to the other side, so to be negative. So it's going to look like that, right? There we are. And then what about this again? What about the point all the way down here? Again, I don't know what that value is. It doesn't matter. All I know is the y value still has to be negative down here, right, somewhere. But the x value has to shift to the positive because the x value changes sign. So it's going to be over there somewhere, right? There we are. So hopefully you see it's not a straight line that we get then. It is a cubic, so it's going to look a bit like that then. There we are. And let me draw that again. It's a bit rubbish. And the point would be about there. Okay. So it comes down like this. Oh, not like that. And then there's a point of inflection at 0 still. And then there we are. Cool. So that's our curve. Okay. Cool. So that is the curve. Y is equal to f of minus x. Right? That's what we sketched by basically flipping the x coordinates to the other sign, right? So if it's negative, it becomes a positive and vice versa. Now let's sketch again compared to the original function. So I'm going to sketch the original function again. So it's going to look like this. If I can get it to look like that. There we are. There we are. That's quite nicely done, in my opinion. Okay, so this would be the graph y is f of x. Okay, which is x cubed again, right? X cubed. There. Okay. So again, what's the difference now? What do you notice with these two functions? Just look at them as their graphs. What do you notice between the black and the red and the green curve? And again, it's going to be fairly similar to what we did with the y-axis, where it's reflection in the x-axis. Well, what's going on here then with these two graphs? Well, hopefully you recognise there's a sort of symmetry going on. But what type? What's going on? Well, hopefully you noticed there's again going to be a particular mirror line, a reflection line. If I get rid of the y-axis, right? Hopefully you see then, if I then draw the line again, the y-axis back here, this is a mirror line, isn't it? The black curve gets reflected into the mirror and it goes to the green curve there. Likewise, down here, the black curve gets mirrored and it reflected through the mirror line, it goes to the green curve over here. So the curves are reflections in the y-axis. So in this case, the opposite occurs. So when we have y is equal to f of minus x instead of minus f of x, this is now a reflection in the y-axis instead, okay? As a very particular type of case of f of a of x, where a is minus 1 in this case, okay? So yeah, cool. So yeah, so whether you want to memorize this and memorize it's exactly reflecting the y-axis, you can. I prefer to just pick some and it will go some examples going over this in a sec. But I just like to pick some particular points, like I've just done, see where they map to, and then connect the curve, and then you should be able to visualize what would be happening, right? Like as we just gone through, right? But yeah, in general, the two main important bits of this section is going to be again these two bullet points here. So I'll go over it one more time. So we have f of a of x for a is inside the function. So like when we're translating, if it's inside, that means you do the opposite to what you expect. So instead of multiplying the x coordinates by a, you divide it by a, or you multiply by 1 over a. On the contrary, if you have the number outside the function, that affects the y value, and you do what you expect if it's outside the function. So in this case, I have a multiplied by my y, so you'd multiply the y values by a. Okay, cool. Okay, let's go over some examples then at last. So we're given that f of x is 9 minus x squared. We need to sketch the curve. First of all, y is f of 2 of x and 2f of x. Now we look at this first, 2 of x. So again, what's going to happen here is it's going to be well, formally, it's what we call a stretch. Well, what to expect is going to happen, right? It's going to instead of well, you'd expect it to times the x values by 2 because it's inside the function. But you do the opposite, so instead you divide by 2, which means the scale factor will be a half instead, because you multiply by half, which is the same as divide by 2. So we call this a horizontal stretch, because remember it has a stretching effect, by scale factor a half. Okay, that's what we formally describe this transformation as. Okay, so then in order to sketch this stretched function, well, we need to see what the original function looks like. So let's sketch this then, right? So f of x is 9 minus x squared. Okay, cool. So obviously let's have our axis here. Okay, and hopefully you realise this is going to be a quadratic, because we have a quadratic expression here. And so when we sketch quadratics, firstly, what type of shape? Is it going to be a smiley positive shape or frowny shape? Well, that coincides with the coefficient of x squared here. Well, it's minus x squared, so minus 1. So it's going to have a negative frowny shape, okay? Then next, well, what's next? Well, then we plot our information on our axis, so our y-intercept and our roots. So firstly, the y-intercept is when x is 0. So then the y-intercept, y, well, it would be 9, right? Because 9 minus 0 is just 9. So it's going to be up here somewhere, okay? Then we need our roots, so that's when you set f of x equal to 0. Well, that means 9 minus x squared is equal to 0. That means x squared is 9. So x is plus or minus root 9, which would be 3. Okay, so therefore our two roots are going to be, say, here and here. Right, cool. Well, then we can plot a quadratic then. So it's going to look like this. There we are. And that's going to be symmetrical because the roots are evenly apart, because we have 3 and minus 3. Okay, so in this particular case, the turning point is at minus 9. And you could see the turning point if you, because this is completed square form, because this is the same as saying 9 minus x plus 0 squared. And hopefully you realise that is completed square form. So then the turning point would also be at, when you set the bracket to 0, well, x would be 0, then 9 outside. So there we are. Anyway, so that's the graph. So then we need, so then we can use this graph to plot the this stretch, right? This stretch graph. So a horizontal stretch again, because it's involving x inside the function. So we're going to times by half. Okay, so do the opposite to what we expect. So you'd think we times by 2, but actually no, we're going to divide by 2 instead. So times by half. So that's what we're going to do. So we're going to times every coordinate, the x coordinate of every point, by half. So then our graph, if we draw it down here, it's going to look like this. Okay, so firstly, let's consider the roots, right? So the x is minus 3 and 3. Well, we're going to need to times by half. We need to halve it because that's our scale factor, remember? So we need to times the x coordinates by half. So 3 times a half is 1.5. So that's going to be 3 over 2. So it's going to be there, roughly there. So the gap, so basically then, the gap between 3 and the origin and 0 is going to be halved, essentially, right? And you can see that here. It's closer to the centre now, to the origin. Then minus 3 over times a half is minus 3 over 2. So it's going to be about there. But then the y-intercept is at 9. That's not going to change because that is when x is 0. Well, 0 times a half is still 0. So that point is not going to change at all. So it's still going to pass through 9 about there. Okay. So therefore then we plot this quadratic curve through the new points. It's going to look like this. There we are. So that would be the graph y is f of 2 of x. Cool. And so hopefully then you see between these two graphs, the original graph on the right corner here, and this graph I've just drawn, it's squashed, right? It's compressed, and that's because you halve the x coordinates, so they're half in value, right? You can see that here because then the graph is a lot more steeper, right? It's less open, as you can see here. The gap here and the gap here is a lot smaller, which means we've compressed it. Okay. And that's what this stretching does, okay? It has that sort of effect. Cool, so that's our graph then. Let's have a look at the next graph I want to draw. So the next graph is y is 2f of x, okay? So the 2 is outside the function. So what's that going to do? Well, it's outside the function, outside the bracket, well, yeah, outside the function. So it does what you expect, okay? So so it affects the y values because it's outside the function, because the input again is not affected. The actual x value, the input in the function, is just x still, so it'll affect the y values. So then we do what we expect. Remember what we talked about at the start. The philosophy is what we do outside the function, we do exactly what we expect. Well, what do we expect? Well, we expect the y to be times by 2 because we're doing 2 times f of x. So that's what's going to happen. So that is what we call a vertical stretch, which again is a fancy way for saying we're going to times the y values, because vertical stretch is basically multiplying the y values. Because vertically, if it vertically is the y-axis, right? So if you're doing anything vertically, it will affect the y values. Anyway, so it'd be vertical stretch with the scale factor of simply 2. Okay, that's what we're multiplying the y values by. Cool, so then that's what we're going to do. So let's sketch our graph. So let's do our axis first. And so what we're going to do then is multiply all the y values of every point by 2 and see what happens. So with the original graph here, well, firstly the roots, the roots, which are the x values of minus 3 and 3, well, that's not actually going to change this time, is it? Because that's when y is 0. If you're on the x-axis, y is 0. Right, again, 0 times 2 is still 0. So the roots will stay exactly where they are, at 3 and minus 3, okay? So they'd still be roughly there. Cool. Okay, but then what about the y-intercept then? Well, the y-intercept at 9, well, that is a y value of 9. So the y coordinate is 9. That's going to need to double then, because we times the y, all the y values by 2, which is our scale factor. So 9 times 2 is going to give us 18. So that'll be the new y-intercept, and that's going to be like all the way up here, right? So then, if we draw the new quadratic, which passes through these new points, well, the 18 now instead of the 9, it's going to look like this. Oh. There we are. There we are. Cool. Okay. There we are. So it's passed through minus 3. Cool. So that's our new graph, and that would be y is 2f of x. Cool. So yeah. The graph looks a bit similar. I guess my sketching doesn't do it much justice. They do look fairly similar, but the graphs are different. I'm talking about the original here. I mean, does it look that different? Not really, but it is a stretch, right? right? Because the y value is doubled, okay? So it is a different graph, okay? As long as you indicate the coordinates, or the coordinates change of what they are, so 9 becomes 18, then it will be clear that you have transformed it in such a way, okay? Um, Also, it is helpful if you are to do more of these graph sketchings. Is online, there's a website called Desmos where you can plot in any graph and it will show you the graph. Why that's helpful here is you can visualize different graphs and see exactly how they change, because you can plot, say, y is f of x. Then on the separate one, you can say y is f of 2 of x, and then you can see exactly what happens with the transformations, and it applies what we've done, and it can help with your learning because hopefully you can spot what happens, and then you plot the graph in and then it does what you expect. So yeah, so I thought I'd give that as a recommendation. It's a very helpful website because it is very helpful to visualize what functions and graphs you are working with, especially later on in the course. But I thought I'd just give that little recommendation, but we'll move on now. Example 13. First of all, it's asking us to sketch the curve y is x of x minus 2, x plus 1. Okay, so again, that's just an ordinary cubic graph. We know how to sketch those. So firstly, we need to determine the type of shape. Well, we need to get the x cubed coefficient. So how do we get x cubed? You do x here times by x there times by x there to get positive x cubed. So it's going to have that sort of shape, okay? So it's going to go upwards. Okay, then we draw our axis over here. Okay, but then we need to find the information, the key information, which are basically the y-intercept and the roots. So firstly, the y-intercept is when x is 0, but if x is 0 into here, into y, I get 0 because x here will go 0, so the whole thing will become 0. So it passed through the origin there. Okay, then I need to find the roots. So the roots will be when when y is 0. So that means when each bracket equals 0. So firstly, the first root is x is 0. Okay, that's the origin. Then we have x minus 2 is 0, so x would be 2. Okay. Then we have x plus 1 is 0, so x would be minus 1 there. Okay. Cool. Then lastly, I need to consider the type of roots we have to really understand what type of the graph would look like. Well, they're all singular roots, okay? None of them are repeated, they're singular. So that means that the line, the curve will just pass through all 3 points, okay? So it's going to look like this. So let's draw it. Oh, not through there. There we are. It's a bit off. There we are. Passes through the origin. There we are, cool. So that's our graph. Y is x of x minus 2, x plus 1. Cool. Okay, part B. It says on the same axis, sketch the curves. Y is 2x of 2x minus 2, 2x plus 1, and y is minus x, x minus 2, x plus 1. Okay, well, these are going to be transformations, but which one? What are we doing exactly? Well, in this instance, when the curves look similar, but you don't exactly know what's going on, just compare it bit by bit, right? So firstly, I have x here, I have 2x, then I have x minus 2 here, then I have 2x minus 2 there, then I have x plus 1, and I have 2x plus 1 there. Hopefully you recognise in each bracket, the x is just 2x instead, right? Well, is that not just the same as saying, if this is equal to f of x, right? This new, oh no, this isn't equal to f of x. The original curve is equal to f of x, say. Then this would be equal to f of 2 of x, right? Because the x is becoming 2 of x. I'm substituting instead of x, 2x into each part. Well, then what's 2 of x? We know what this would be. this would be, well, what would it do? Well, again, you do the opposite to what you expect if it's inside the function. So instead of timesing by 2, the x values, you divide by 2. And so that what that would look like is a horizontal stretch. So again, that's a stretch that affects the x values by scale factor. So what we times them by, right, it's not going to be 2, it's 1 over 2, which is the same as divided by 2, okay? And so, yeah, that's what it's going to look like. So we can use our original curve and then basically divide the x coordinates by 2 to see what happens, because the scale factor is the half, you times the x values by half. Okay, but it's said on the same axis, so I'm going to need to sketch this curve as well after. So I'm going to need a big curve. And I'll tell you what else I'm going to do. I'm going to draw both curves in different colours as well. So let's draw this curve in... Nope, let's draw this curve in... Let's draw it in orange this time. There we are, no particular reason, just orange. So what's going to happen then? I need to times the x coordinates by a half. So I need to half the x coordinates. So firstly, this one at -1 would then be minus a half. So it's going to be really close to the origin. It's going to be like there. And then the origin will still be the origin because half of 0 is 0. So I'd label that as minus a half. And then this point 2 would then go to 1. Half of 2 is 1. Okay. So then our cubic needs to be squeezed in, right, in order to pass through all these curves in the same way. So it's going to look like that then. It's so close, it's just approximating it as a line. Okay. There we are. There we are. Okay. So that's our new curve. So it's a lot more packed in. Okay. You have to squeeze it in a bit more in order to pass through the points when they're closer together, because we halved the x values, which means they're together by 2 essentially, by a factor of 2. So it's a lot more squeezed in, and that means it makes the curve steeper as well. So you can see here at this point it's a bit less steep compared to this part here, and it has to be steep because we're basically compressing the whole graph, which is what we do when we're doing a stretch of a half here. Okay, so that is going to be the graph y is 2x of 2x minus 2 of 2x plus 1. Okay, cool. Then for part C. Oh no, it's still part B. Let's go back to black. It's then asking us to sketch y is minus x of x minus 2 x plus 1. Okay, so again, what's happening to this graph compared to the original up here? So, well, again, you can compare, but hopefully you see the only difference is there's a minus here, but there's nothing there. The only difference is a minus. Well, what that's saying is you're timesing the whole thing by -1. So if this is f of x, this curve would be minus f of x, right? You're multiplying the whole thing by -1. So that's the curve we're sketching, is that would be equal to minus f of x if we called the original curve f of x, say. But what's that going to do? Well, you could remember it as a reflection, but let me go over kind of how to almost derive it. Well, instead, what we'd say is a vertical stretch, which means basically, again, you multiply the y values by scale factor -1. So again, you do what you expect, you times by -1, okay? So let me then draw in purple, sorry. So what that means is all these points, the key points I've drawn here, they or any other points actually on the curve, all the points on the curve, the y values have to flip sign, okay, essentially. If you multiply by -1, you flip the sign, Okay, so let's start with these points, these 3 points. Well, they're roots, aren't they? That's when y is 0. If y is 0, then negative 0, so is 0. So these 3 points will remain exactly where they are, actually. So minus 1 would be there. Then I have 0 here, which is the origin. So that doesn't change. Then the other root is 2. So then that would be double where 1 is, so it'd be there. Cool. Then, okay, well, I don't have enough information to sketch it, really. So let's consider some more points. Well, what about this point here? This is a turning point. That's on the positive y-axis, so that's going to go down to negative y down here, isn't it? So that turning point is going to go from there to actually down there somewhere, okay? Then what other points stick out? Well, what about this end point down here? Well, that has a negative y value there, so it's going to go up all the way, to the positive y value there, isn't it? So that point needs to be transformed to over here instead. No, to this point. Sorry. Okay, because the y value again needs to become positive. Okay, so negative y value becomes a positive. So we need to that point needs to go up here. So it would look looks like it would be there somewhere. Okay. So all I've done is at this point on the negative y, which is kind of like the end point almost. Obviously it continues on the graph, but it's a cut-off point for my graph anyway, the way I sketched it. The end point, which is all the way down here, the negative y-axis, will then be all the way up here and the positive because the sign flips. So it'd be there. Likewise then, let's consider the end point here. So this point would then again have to go to flip signs on the y-axis. So it goes from here to all the way down here to flip signs, so it'd be there instead, okay? So therefore that point on this graph would look like it's there somewhere, right? Okay, well now I actually do have enough information to have a good rough idea of what my graph would look like if I sketched it. Oh, I didn't mean to do that. Let's sketch it again. There we are. Okay, I didn't mean to delete it, but there we are. So let's connect these dots then, right? These purple dots, as to look like a cubic. So originally, I'm pretty sure I drawn a point down here, didn't I? Where did my point go? You know, yeah, this point here was meant to go up here somewhere. I don't know where that went. Yeah, so again, this point here, it goes to the positive y value, so it'd be up there, which is there. Don't know where that point went, beyond me. Anyway, so now let's connect these dots with a nice cubic curve. So it's going to look like this. It's going to come down here, then it's going to turn your point there. It's going to go through the origin, and then it's going to cut through too. There we are. That should be our curve. Okay, and again, you could do this turning point, and that should go up there. That corresponds to this turning point there. Okay, cool. So there we are. So that's our graph then. So that would be y is minus x of this curve here. So minus x minus 2, x plus 1. Okay. So all we've done there to help us sketch it, we looked at particular points on the curve and we saw where they would go to under the transformation. So in this case, under when the y values will flip sign because you timed it by minus 1. So that's our purple curve. So those are our two curves, and again you recognise hopefully that the purple curve, alternatively you could say, actually this is a reflection although it doesn't look like reflection, but it is a reflection under the x-axis, right, of the original black curve there. You reflect the black curve in the x-axis, you should get a graph that kind of resembles the purple curve there. Okay, cool. So therefore we could also say or reflection in x-axis. Okay, but me, I don't really need to memorize that particularly, because I can kind of almost derive it by just using this and realizing I could just multiply by -1 and then see what happens, and I notice we get a reflection. Okay, cool. This question then. On the same axis, sketch the graphs of y is f of x and y is f of minus x and minus f of x, where f of x is x of x plus 2. So, okay, firstly we should probably sketch this, right? So it's all on the same graph, so we're going to need an absolutely massive graph, right? There we are. Because we're going to have 3 different curves on it. It's going to be a lot of action on there. So f of x, firstly, y is x of x plus 2. Or we could call it f of x, right? Okay. So, oh, that's plus 2, not plus 1. There we are. Now, again, that's a quadratic, so we should know how to sketch quadratic. So firstly, it's going to have a positive U shape, a smiley shape, because we have positive x squared, right? So the x squared coefficient's 1, which is positive. Then we need to find the y-intercept, so that's when x is 0. But if x is 0, f of x is 0 as well, which is y, because we have a 0 for x there. So the whole thing multiplies by 0 to get 0. Then we need to to find the root, so f of x equals 0. That means either x is 0 or x plus 2 is 0, which will mean x is minus 2. So it's going to go through x is 0 or x is minus 2 there. Okay, cool. So those are roots. So then we can sketch a graph for it. So it's going to, by looking like that, it's going to look like this. There we are. And that would be y is f of x. Okay, now it's asking us to sketch y as f of minus x. Now again, f of minus x, you could do 2 ways. You could jump right into saying what type of reflection it is, because it's going to be a reflection again. But let's just try and find some testing points out, okay? So, well, the other way of writing this is going to be what we call a horizontal stretch by scale factor. And it's horizontal because it affects the x values. Remember, x-axis is a horizontal line, so that's what that means. And scale factor, well, it's not going to be minus, well, it is, but we'd expect it to be multiplied by -1, but instead you're going to divide by -1. So the scale factor would be 1 over -1, but actually that's still -1 in this case, okay? So what that means is the x coordinates are being multiplied by -1. So then I'm going to do it in a different colour. Let's do it red again. So I need to multiply, basically flip the sign of all the x coordinates, right? To become, if they're negative, they become positive, and positive become negative. So let's have a look at these 2 roots again. So this is x minus 2. So if I'm times it by -1, which is my scale factor, that means it needs to come to positive 2 over here, right? And then likewise 0, well, it'll still be at 0 because the origin, because obviously 0 isn't affected by -1. So therefore the new curve that passes through these 2 points, and again this point here, if it's say negative, well, I don't know where that is, but this turning point is on the negative x-axis. That turning point would then move over here to the positive x-axis in the same sort of distance, okay? So if it passes through the origin here and these 3 points in the same sort of quadratic curve there, if I draw a nice quadratic curve passing through these 3 orange points, then the curve is going to look like this. There we are. Lovely stuff. And that's going to be a curve. Y is f of minus x, right? Now, alternatively, hopefully you notice again, this is a reflection in the y-axis between the black and the orange curve. Okay, that's what's going on there. So alternatively, you could say, or reflection in the y-axis. Okay, cool. Then our other curve is actually, the other one it wants us to sketch is minus f of x. Okay, so then minus f of x, well, that's going to be a vertical stretch because the minus is acting outside the function, so it affects the y values, and the y values, the y-axis acts vertically up. So it's a vertical stretch, which means it affects the y values by scale factor. Well, -1, right? Because you do what you expect. You multiply by -1, that's what happens. Okay. So again, I'm gonna try and pick some y coordinates then, or some points on the original black curve, and then I'm gonna see whether, and they're gonna flip the y values, right? So let's have a look. So firstly, the roots. Well, the roots are at the original root. So I'm looking at the black curve, which is the original function. I have -2 and 0, which are the two roots. Obviously, that's in orange, but it's also in black. Well, the roots will stay where they are because that's when y is 0. If y is 0, that's unchanged because 0 times the -1 will still be 0. So it would still this purple curve that I'm transforming, which is minus f of x, it will also have to pass through the two roots there. Okay, cool. Then, okay, let's find some other points on the that we know will be transformed into to get a good idea of what a purple curve will look like. So, let's a good idea is to consider this turning point here, right? Well, this point here is negative y down here. I don't know what value it is, it doesn't matter. I'll just know it's negative y there. So it's going to go up to positive y, and it's going to be about there, okay? If I kind of match the distance between the origin, between the axis, right? Same distance there and there, roughly. But the idea is to flip it to a positive, okay? Cool. Okay. Okay. Well, actually, I have enough. I think I have enough information actually. But to be extra safe, let's consider the other point. What about all the way up here, right? Well, here, that's over here. That's a positive y value. It's going to come all the way down to the negative y-axis down here, right? Remember, the x coordinates stay the same because we're not changing the x coordinate, just the y coordinate, so it would be there instead. Okay. And then up here again, that would come down here somewhere, okay? So that'd be the transformation of the circled point originally. That's that point transformed. So the y value again flips sign from positive to a negative. So now let me connect all these y points here to form another sort of quadratic curve. So there we are. So let's draw it then. So it's going to look like this. There we are, great. And that'll be y is minus f of x, okay? Cool. And again, compared to the black curve, hopefully you recognise again that this is going to be reflection in the x-axis, right? If you compare the purple curve to the black curve, right? It's reflected in the x-axis. So again, like here, this part here, that's the reflection in the x-axis. Cool. Again, this here, the turning points of the black and the purple curve are reflected in the x-axis. So yeah, cool. So then overall, this is also reflection in the x-axis. Okay, depending on what you want to do. But there we are. That's the alternative. Cool, and they're the same thing, right? So the two different ways of expressing the same thing in this particular case. Okay, cool. So let's have a look at some more examples then. So first of all, question A, it said the point Q, which is -2, 8, lies on the curve of equation y is f of x. State the coordinates of the point Q is transformed into on the curve of equation y is f of a half x. So in this new transformed curve, where does this point go to? Okay, and again, so let's consider, so is this half of x, right, is inside the function, so it affects the x, but also it does the opposite to what you expect. So in this case, it would be what you do the opposite of what you expect. So you would expect to times by a half, but instead we call it a horizontal stretch by scale factor. Well, scale factor, instead of timesing by a half, you divide by half. Well, a half, it's 1 over 2. But then if you compute that, 1 divided by a half, you KFC, 1, and then you change the sign to a times, and then you flip the fraction to 2. Well, it becomes 2, okay? So if you divide by a half, that's the same as times it by 2, okay? So that's what we got then. So that's saying effectively this is timesing the x value by 2, okay? Or dividing the x coordinate by half. They're the same thing. So then that means minus 2,8 under this transformation has to go to the point, well, minus 2 times 2. Okay, that's my scale factor horizontally, which means x, right? It affects the x values. And so the x value is being times by 2, so I have to times the minus 2, which is the x coordinate, by 2, the scale factor. And the y coordinate will remain at 8, because there's nothing going on outside the function itself. So the y value will remain unchanged. So we can simplify that then to minus 4,8, and that is your transformed point. Cool. Question 9. Part A. It's asking us to sketch y is x minus 2, x minus 3 all squared. So that's going to be a cubic, and again we should know how to deal with cubics. So firstly, what type of cubic graph? Is it that sort of shape, or is it going to be that sort of shape, positive, negative? Well, let's look at the x cubed part. So how do we get x cubed? We do x times x, but this will be x squared because it's the same bracket twice. So that would give me positive x cubed, so have that sort of shape. Okay, cool. Then let's draw our axis. So let's draw our cubic shape. Well, then I need some key details. So the y-intercept and the roots again, as usual with sketching. So the y-intercept would be when x is 0. Y would be, if I plug in 0 into all of this, you get 0 minus 2, 0 minus 3 all squared. That would be minus 2 minus 3 squared. And that would give me, if I put minus 3 times minus 3, positive 9 times minus 2, you get minus 18. Okay, so the y-intercept will be all the way down here, actually at like minus 18. Okay, then I need the roots. So the roots are at x is 2, so it'd be about there somewhere at 2. No, let's draw it a bit further outwards. There we are. 2 there, and the other one would be x minus 3 is 0, so x would be 3. Okay, so those are my two roots. Okay, so then I need to look at the type of roots. So I have a single root at 2, it's a single bracket, but this is a double bracket, so it's a double repeated root. So at 3 it's going to touch the axis, so it's going to look like this then, and it's going to touch the axis at 3. So with that all in mind, my graph is going to look like this. And it's going to touch it there, and then it's going to bound back up. Cool, so that's my graph. Y is x minus 2, x minus 3 all squared. Cool, then for part B, the graph of y is ax minus 2, was it? And yes, and ax minus 3 squared. passes through the point 1, 0. Find the two possible values of a. Now, we did look at a very similar example to this last video where we looked at translations, but we can do it with this sort of transformation as well, with stretching. So it passes through the point 1, 0, but again, what's happened to this curve? What is the difference between this one and that? What's the relationship, the link? Well, let's compare part by part. So I have x minus 2 here. I have ax minus 2 there. Okay, then I have x minus 3 squared. I have ax minus 3 squared. So the x's again are just being changed to ax. So all the x's are being multiplied by a. If I was to express this as f of x, well, ax minus 2, ax minus 3 squared, that would be equal to f of ax, wouldn't it? Right? And so that would be what we then call a horizontal stretch. Remember, so what we do inside the bracket, we do the opposite to what we expect. So instead of multiplying the x values by a, I divide it by a. So that would be a horizontal stretch, a scale factor, which means what we multiply the x values by is not a, it's 1 over a. Okay, which is the same as divided by a. Okay, alternatively again, what that also means, and it can be helpful to think of it in terms of this, any coordinate x, y, if the x coordinate is being multiplied by 1 over a, the new coordinates on the graph will be 1 over ax, or a over x, I guess, or x over a, sorry, and y. Okay, because then that's saying the x coordinates have been divided by a, and the y value stays the same. That's effectively what's going on. Okay, now I need this new transformed curve to pass through 1, 0. It's going to go through, if I draw it in red or orange here, it's going to pass through here, right, which would be 1, 0, okay, the orange point. So I need this transformation where I basically divide the x values, or multiply the x values by a certain number, to then go through 1, 0 here. Now, if I'm just multiplying the x values, I'm not changing the y values, so it has to be on the x-axis, because that's when y is 0. That's going to correspond to these 2 points somehow being stretched to 1, 0, okay? So what that means is I need to multiply the points 2 and 3 here, the roots, by a number a, 2 or 3 times a to get to 1. So what that means is I need, firstly, let's consider the point 2, 0, which is the first root. I need that to go to 1, 0. Well, how am I going to get to that? What am I timesing 2 by to get to 1? I'm going to times by a half, aren't I? Because then 2 times a half will get me 1. Well, that means the scale factor is 1. The scale factor in this case is going to be a half, because that is what I'm multiplying the original x coordinate of 2 by to get to the new coordinate of 1. So I'm dividing 2 by 2, or timesing 2 by a half to get to 1, which is my scale factor. Now I said the scale factor is 1 over a, so actually therefore a is simply 2. Okay, if you just compare, okay, that fraction and this fraction there. Okay, that might be. This is a hard question to get your head around. But hopefully you recognise all this is doing ultimately is I'm basically dividing the x coordinates by a, essentially. So what I want to do is find the roots and divide these 2 roots. What number divides 3 to get to 1, essentially, or 2 to get to 1? Well, in this example, 2 divides by 2 to get to 1. So my scale factor is a half, because it's divided by 2, so a would be 2. We're going to do the same with the other root. The other root is at 3, there. So now I want 3, 0 to then go to that new point 1, 0. I want to transform 3, 0 to 1. So again, I need to do that by a scale factor of 1 over a. Well, a scale factor. Well, how am I going to get from 3 to 1? What am I multiplying 3 by to get to 1? It's going to be a third, isn't it? 3 times a third is 1. So that's my scale factor, which is my horizontal stretch, right? Which means what am I multiplying my x values by to get to the new point 1? right? It's going to be a third. Therefore, if I compare again with these fractions, a is 3. Okay, cool. And there we are. So those are the only two values. Because again, if we are not changing the y value, which means if I want my new point to be at 0 for the y value, that means the old point has to be at 0 too. But the only points with y equals 0 again are the two roots. So the only way I can get the new point 1 0 is if the old points are at 1, I have y value of 0 as well, and then times the x values by something to get to 1, and that's what I did. So these 2 points again are at 2 0 and 3 0. So I did 2 times a half to get to 1 and 3 times a third, and that gives me my multiplier, my scale factor, which would be 1 over a. There we are. Cool. And therefore the function then would be f of 2 of x. That's what I would need to sketch to get that curve to 1 0, or f of 3 of x, right? To then do the same thing there. Cool. So those are my two a values. Okay, and there we are, and that's it. And yeah, it said 2 values, so yeah, there we are. That's our question done. Cool. So yeah, that is stretching. So again, it's the exact same philosophy, right? The whole idea underpinning this, right, as complicated as it might seem, is that fundamentally what you do inside the function, so f of a of x, like with the previous section, f of a of x, instead of multiplying by a, you divide x by a, right? That's essentially all it is. And af of x, instead of, well, you do what you expect because it's outside the bracket, or the function, so you do multiply. And because it's outside, it's the y that gets affected. So multiply y by a, and that's what you expect because you timed in f of x by a. There we are. So that is stretching. So yeah, stretching graphs even. So yeah, that's it for now. I'll see you soon.